I'm going to take a look at how we would run a quick regression analysis in SPSS. This is not an in-depth look, and I'm not going to look at the residuals. This is just a getting started video. Anyone that wants to take it further, you'll need some more information, but we're not covering it in depth in this course. So we want to answer the question, is there a relationship between BMI and body fat percentage? And if there is, how good is it? This is not the actual data from the paper, it's just data that I've created to look a bit like it for comparison. So when we're running a regression, the things that we're interested in is, are the variables continuous, which they should be and they are? Is the relationship linear, that is a straight line a good fit? Are there any outliers which could be having a strong influence on this line? Are the observations independent? Are the variances homoscedastic? Are they similar across the fitted line? And are the errors normally distributed? And that bit we won't really be looking at. So if we do a scatter plot of this graph, we can see that a straight line seems okay. It's not perfect, and maybe a curved line would fit better, but this will do as a starting point. When you're in SPSS, you can double click on your graph to get the fitted line put on it, and you can also add these confidence lines. So you can just see them very faintly in green here. These are our confidence bands. On a lot of graphs you'll see in papers they're shaded rather than being extra lines. And the other thing we get is the actual equation printed out on top of the graph. It will automatically tell us the R squared over to the side of the graph, and if you remember, this lies between 0 and 1, where 1 would be a perfect relationship and you would see all the dots lining up along this fitted line here. But this is not a perfect relationship, and so our R squared is not close to 1, it's getting close to 50%. So normally this would be pretty good, but if we're actually trying to use BMI to predict body fat percentage, then perhaps this is not high enough. So it's common practice to put the independent variable on the x-axis and the outcome on the y-axis. Because we're trying to predict body fat percentage, we would consider this the outcome in this case. Mathematically, it doesn't really matter which way around you put it. You'll get the same R squared out. It'll just make a difference to how you interpret the equation. So next we might look at outliers. This one looks like an outlier. It's towards the middle of the line. Well, technically if we go up, it's not in the middle of the line, but it's not right on the edge, so I don't think it'll be having too strong of an effect. SPSS will give us a warning when we run the analysis though, if this is having a strong influence on the line. It's possible it could be tugging the line down a little bit, but because there's so much data here, I'm not sure that this one would be strong enough to have a lot of influence. And also this green one, again, will be having a little bit of influence, sort of tugging the line towards it. Between the two of them, I'm not really sure that they're going to be a problem. Are the variances same across the fitted line? So I've drawn this in some sort of very rough blue lines, and we can see that there's a little bit less variation down here than there is up here. This is not too strong, so I wouldn't be too worried about it. It's probably just because there's more variation in the higher ranges and there's actually fewer women who are underweight than overweight. So you can do all of that on a graph before you even run the analysis. Once you want to run the analysis, there's a few different ways you can do it in SPSS. The one that I like is if you go to Analyze General Linear Model and then Univariate, just because this gives you more options for extending the model later. It's much easier to add extra variables in. If we have a look at the boxes, our dependent variable here is the body fat, and our covariate is BMI. And then if we click on options, we get a few extra things we can tick. We might want the estimates of the effect size. We're not really covering that in depth, but a couple of people have asked about these eta squareds or partial eta squareds. We probably would want to have a look at our parameter estimates if we wanted to write an equation for this. And there are some options here for doing residual plots, which we're not going to cover. Looking at the output, I recommend probably that you look at the estimates of the parameter estimates. I was looking at the output while talking, which is never a good thing. So this first one is around how the model was built, and you can see the significance values over here. But if you actually wanted to write down the equation, you would want this second table with the parameter estimates. I don't think my arm likes bending. Oh, it's going to bend, it's going to bend. Yep, I've completely dislocated my shoulder. So if we wanted to write this equation out, we would say body fat is equal to about 10 plus 1.1 times the BMI. So for every 1% increase in BMI, we're getting around a 1.1 increase in body fat percentage. And both of these parts of the equation are significantly different from 0, is what that is telling us. And you can see that's been done with a t-test. So if you have read up on effect sizes, I'm going to guess most people haven't, but there might be a few that have. That's this partial eta squared, and that gives us a measure of how big the effect is. In this context, we're probably not so concerned with that, just because we're looking at the strength of the relationship between the two variables, but in other contexts that might be more important. So we're not going to cover the residual analysis in this course. If you want to try it, you should tick that box to save your residuals, and then if you want to see more, I'm very happy to demonstrate that in the workshops. So the last thing we might want to do just for this simple example is think about how do we split for the genders, because as we saw in the paper, there are actually two different sort of lines for the men and the women, because on average females have a higher body fat percentage than males. You can do this in SPSS in the graph. You can say fit at subgroups, I think that's what it says, and then you get these two separate lines, but you have to have done the scatter plot, which allows you to colour by groups in order to do this. To run the analysis, this is where the general linear model option comes in handy, because we have this box here to add in fixed factors. If we wanted to adjust for another continuous variable, we would pop it into the covariate box. Anything which is in categories will pop into the fixed factor box. And for this course, you can just ignore the random factors. So we've got body fat percentage with BMI adjusting for gender. Then if we have a look on our output, I'll come a little bit further away so I can point better. Again, we've got our intercept and BMI, and now we've got this little adjustment for female. So that means if you're a man, you don't need any adjustment. The base equation will work for you. The men are the reference level, and then we've got an adjustment for women, and that's about an extra 11% added onto their body fat percentage based on their BMI. So finally, you might be interested in fitting a curve. Now, we're not going to cover actually running the regression with the curve, but you can have a look at it if you're interested just in SPSS. When you double click on the graph and you have that option to fit the line, you probably would have seen that there was the option to fit the curve as well. And so you can add that on there, and you'll see now we're actually getting very close to what they had in the paper. And that was the paper, just as a reminder. Plus they did also adjust for age, which we haven't added in here, and this is the comments I've stuck below is from that data analysis box where they actually gave us the equation for their line.